During the Second World War, a guided weapon was developed that combined high explosives with live animals, formal laboratory conditioning, and operational military testing. The system was designed to strike hardened targets with a level of precision unavailable to conventional munitions of its time. It was funded, classified, engineered, and trialed under official authority. Its guidance system was biological, not mechanical. Its operators were not soldiers, but trained pigeons. The existence of this weapon challenges the conventional narrative of wartime innovation. It contradicts the assumption that guidance technology in the 1940s was limited to gyroscopes, radio control, or optical tracking devices. It demonstrates that military research institutions were prepared to abandon orthodox engineering logic when standard solutions failed to meet strategic demands. The weapon did not rely on electronics, did not require external signals, and did not depend on human operators after launch. It relied entirely on conditioned animal behavior. This system was not a speculative concept or an anecdotal experiment. It reached the stage of functional prototypes, controlled testing, and formal evaluation against real-world military requirements. It was assessed as accurate under laboratory conditions and resilient to certain forms of countermeasure. Its cancellation was not the result of technical impossibility, but of shifting priorities and institutional discomfort. The paradox embedded in its design is direct and unresolved. A modern industrial war produced a precision weapon guided by instinct, reward conditioning, and biological reflex. The missile was deadly by design, methodical in concept, and treated as a legitimate solution to a critical operational problem. Yet it has remained largely absent from mainstream accounts of the war. Despite meeting the same criteria as other classified weapons programs of the period. This weapon existed, functioned, and was taken seriously. Its story exposes a dimension of World War II research that is rarely acknowledged and rarely discussed. By the early years of the Second World War, industrialized states were engaged in a conflict defined by scale, speed, and material intensity. Strategic bombing campaigns expanded rapidly, naval warfare extended across entire oceans. And fixed industrial targets became central to national survival. Factories, shipyards, fuel depots, and power stations were no longer peripheral objectives. They were decisive nodes in a war of production. Conventional weapons struggled to meet the demands imposed by this environment. Unguided bombs depended on altitude, weather, crew training, and statistical saturation. Even massed bomber formations produced low accuracy against hardened or compact targets. Naval artillery faced similar limitations when engaging maneuvering ships or defended coastal installations. The result was an increasing gap between destructive capacity and actual target precision. At the same time, technological solutions to guidance were immature. Early radio-controlled weapons suffered from signal interference, limited range, and vulnerability to jamming. Mechanical guidance systems lacked responsiveness and reliability. Optical tracking demanded line-of-sight conditions rarely available in combat environments dominated by smoke, flak, and weather. Each approach imposed logistical burdens and required scarce components, skilled operators, and extensive training pipelines. Resource constraints compounded these problems. Electronics production competed with radar, communications, and cryptographic systems. Skilled technicians were in short supply. Manufacturing tolerances for miniature control systems were difficult to maintain under wartime pressure. Strategic planners required weapons that could be produced rapidly, deployed flexibly, and operated with minimal external support. Within this context, unconventional research gained institutional acceptance. Military laboratories were encouraged to explore non-standard solutions when orthodox engineering failed to produce results. Psychological warfare units, sabotage branches, and special research divisions expanded their mandates. The boundary between scientific experimentation and operational weapon development became increasingly porous. Sabotage and covert action played a critical role in this shift. Attacks on infrastructure behind enemy lines demonstrated that small Precise disruptions could generate effects disproportionate to their physical scale. Disabling a single facility could halt production chains, delay deployments, or force costly defensive reallocations. Precision, not tonnage, became the limiting factor. This environment created space for approaches rooted in behavioral science rather than mechanical engineering. Animal navigation, homing behavior, and conditioned response were already subjects of civilian research. Military institutions recognized that these biological capabilities operated independently of radio signals, power supplies, or human intervention. They functioned in darkness, through smoke, and under stress. They required food rather than fuel and training rather than circuitry. The strategic logic was not eccentric. It reflected a systematic evaluation of available resources and constraints. If machines could not reliably guide a weapon to its target, and if humans could not remain in control through the terminal phase of an attack, then an alternative guidance system was required. In that analytical space, biological guidance became a plausible solution. The Pigeon-Guided missile emerged from this environment. It was not an anomaly detached from wartime logic. It was a direct response to operational failure, technological limitation, and strategic pressure. Its development reflected the willingness of World War II military research to subordinate convention to effectiveness, regardless of how unconventional the resulting weapon appeared. The Pigeon-Guided missile was developed in the United States under a classified research effort led by psychologist B.F. Skinner. The program was formally supported by military research authorities and integrated into broader investigations into guided munitions. Its development was grounded not in speculative theory, but in experimentally validated principles of animal conditioning. The central design premise was direct. Certain animals possess innate navigational and visual tracking abilities that surpass contemporary mechanical systems in reliability under adverse conditions. Homing pigeons, in particular, demonstrated exceptional target fixation, motion tracking, and directional persistence. These traits were already well documented and reproducible in controlled laboratory settings. The project sought to convert these biological functions into a functional guidance system for an explosive weapon. The missile's structure was deliberately simple. A conventional explosive payload formed the primary body. At the forward section, instead of a mechanical seeker or optical sensor, a transparent nose cone housed one or more pigeons. The birds were positioned facing forward, with their heads restrained but their necks and eyes free to move. A projection screen was mounted directly in front of them, linked optically to the external field of view. The guidance logic depended on conditioned behavior. Each pigeon was trained to recognize and respond to a specific target image, such as the silhouette or outline of an enemy ship. During training, the bird was conditioned to peck at the image whenever it appeared centered in its visual field. Food reinforcement was used to reinforce this behavior until it became automatic and resistant to distraction. In flight, the projected image of the external scene appeared on the screen. When the missile deviated from its intended trajectory, the target image shifted away from the center. The pigeon instinctively pecked toward the image. These pecking motions were mechanically translated into control inputs. Sensors detected the direction of each peck and converted it into corrective adjustments to the missile's control surfaces. Redundancy was built into the system. Some configurations used multiple pigeons operating simultaneously. Their inputs were averaged, reducing the risk of individual error or fatigue. This approach addressed concerns about biological variability and ensured stability in guidance behavior. The design intentionally avoided complexity. No electronic processors were required. No external signals were transmitted. No human intervention was possible after launch. The system functioned autonomously from release to impact. This isolation made it inherently resistant to electronic countermeasures and signal disruption. The apparent strangeness of the design masked a rigorous military logic. Mechanical guidance systems of the period failed under vibration, shock, and environmental interference. The Pigeon-based system exploited an adaptive biological processor capable of real-time visual interpretation. Its simplicity reduced manufacturing demands and eliminated entire classes of technical failure. The weapon's design did not seek elegance or innovation for its own sake. It sought reliability under wartime constraints. The choice of pigeons was not symbolic or whimsical. It was the result of systematic evaluation of sensory acuity, training efficiency, and operational resilience. Every aspect of the system reflected an intentional trade-off, abandoning technological orthodoxy in favor of functional effectiveness. The Pigeon-Guided missile was not confined to theoretical design or laboratory abstraction. It progressed into structured testing programs intended to evaluate operational feasibility under conditions approximating combat use. These tests represented the transition from research concept to deployable weapon system. Even though full-scale battlefield employment never occurred. Initial deployment occurred within controlled military research facilities. Prototype glide bombs equipped with the Biological Guidance Unit were mounted on test rigs and release platforms. The objective was to replicate the terminal phase of an attack against a maritime target. The environment for which the system was primarily conceived. Enemy surface vessels were selected as the reference objective because they combined high strategic value with limited maneuverability during approach. During early trials, the missile body was released along a predefined glide path toward a visual target. The pigeons, already conditioned to recognize ship-like silhouettes, were enclosed within the nose compartment prior to release. Upon exposure to the external visual field, their behavior transitioned immediately from passive to active guidance. Observers recorded consistent pecking behavior aligned with target displacement on the projection screen. The causal chain was direct and measurable. When the missile drifted off axis due to aerodynamic instability or wind, the projected target image moved. The pigeons responded by pecking toward the offset. The mechanical linkage converted this motion into corrective control inputs. The missile adjusted its trajectory accordingly. When alignment improved, pecking frequency stabilized, maintaining course until further correction was required. Testing data demonstrated repeatability. Multiple runs under similar conditions produced comparable guidance behavior. When redundancy configurations were employed, disagreement between pigeons resulted in dampened control inputs rather than erratic movement. This averaging effect improved stability and reduced oscillation, addressing early concerns regarding biological inconsistency. One documented deployment scenario involved simulated attacks against scaled ship models placed within visual range of the test platform. These models were stationary but visually representative. The missile prototypes consistently corrected their flight path toward the intended aim point. Impact accuracy exceeded that of unguided glide bombs tested under similar conditions. The system's resilience was also evaluated. Vibrational stress during release did not suppress condition behavior. Changes in lighting affected performance minimally, as the pigeons relied on shape recognition rather than color or fine detail. Environmental noise and motion did not disrupt the guidance cycle. The Biological Guidance Unit functioned continuously until simulated impact. Despite these successes, operational deployment beyond testing environments faced institutional barriers. The system required pre-launch preparation that differed from conventional munitions handling. Live animals demanded care, feeding, and conditioning cycles incompatible with standard ordnance storage protocols. Command structures accustomed to mechanical reliability expressed skepticism toward biological components, regardless of empirical results. As competing guided weapon projects advanced, particularly those employing radar and improved mechanical systems, strategic emphasis shifted. Resources were reallocated toward technologies perceived as more scalable and institutionally acceptable. The Pigeon-Guided missile was formally discontinued before combat deployment orders were issued. The termination was procedural, not reactive. No catastrophic failures prompted cancellation. No decisive test invalidated the core concept. The program ended as a result of changing priorities, not operational collapse. Its deployment phase concluded with the system validated but unused, existing in the narrow space between functional weapon and historical footnote. The missile was therefore deployed in a sense recognized by military development doctrine, constructed, tested, evaluated, and prepared for potential field use. Its absence from combat does not negate its operational maturity. It represents a weapon that reached the threshold of use, then was overtaken by alternative solutions before that threshold was crossed. The Pigeon-Guided missile exerted influence beyond its physical specifications, despite never entering active combat service. Its strategic and psychological impact emerged from what it represented within the military research establishment rather than from damage inflicted on enemy targets. The program altered assumptions about guidance, control, and the boundaries of acceptable military experimentation. Within internal evaluations, the system forced a reassessment of reliability. Traditional weapons were judged primarily by material robustness and mechanical precision. The Pigeon-Guided missile inverted this logic. Its guidance core was adaptive, self-correcting, and tolerant of disruption. This challenged entrenched engineering hierarchies and exposed institutional bias against solutions that could not be reduced to metal, circuitry, and schematics alone. The existence of a functioning biological guidance system complicated enemy countermeasure theory. A weapon immune to radio jamming, signal interception, and electronic deception occupied an uncomfortable strategic category. Defensive planning relied on predictable technological dependencies. The Pigeon-Guided missile removed several of those dependencies entirely. Even in theoretical assessments, this absence of exploitable vulnerabilities elevated its perceived strategic value. Psychologically, the concept introduced uncertainty. Military planners were accustomed to anticipating adversary capabilities through industrial indicators such as factory output, material shortages, and technological bottlenecks. A weapon guided by trained animals bypassed those indicators. It relied on behavioral conditioning rather than rare materials or specialized manufacturing. This reduced the transparency of production and complicated intelligence estimation. The system also highlighted the extent to which total war dissolved ethical and conceptual boundaries. Animals were not merely logistical assets or messengers, but integral components of lethal systems. This integration reflected a broader wartime pattern in which all available resources, biological and mechanical alike, were evaluated for weaponization. The missile's impact lay in how far it extended that logic, not in the scale of its explosive yield. Strategically, the program demonstrated that precision effects could be pursued independently of technological maturity. The missile achieved terminal guidance accuracy through means unrelated to industrial advancement. This reinforced the principle that effectiveness could emerge from unconventional synthesis rather than linear technological progress. Although discontinued, the program influenced internal doctrine. It validated the exploration of non-traditional guidance paradigms and expanded the conceptual toolkit of military research institutions. Its legacy persisted indirectly, shaping openness to hybrid systems and interdisciplinary approaches during the latter stages of the war. The psychological weight of the Pigeon-Guided missile resided in its contradiction. It was small, silent, and biologically driven, yet it addressed strategic problems that massive industrial systems struggled to solve. Its impact exceeded its physical presence, existing primarily in the realm of institutional thought rather than battlefield destruction. The Pigeon-Guided missile occupies a distinct position in the history of World War II weapons development. It was neither an improvised curiosity nor a marginal experiment detached from strategic necessity. It emerged from formal military research structures, responded to clearly defined operational deficiencies, and progressed through recognized stages of weapons evaluation. Its cancellation does not diminish its historical relevance. Instead, it defines the limits within which wartime innovation was ultimately constrained. This weapon reflects a period in which effectiveness outweighed convention. Faced with the failure of existing guidance technologies, military institutions authorized solutions that drew from psychology, ethology, and behavioral science. The Pigeon-Guided missile stands as evidence that World War II research culture tolerated radical departures from engineering orthodoxy when strategic pressure demanded results. Its significance lies in what it reveals about wartime thinking. The system treated biological organisms as functional components, governed by predictable responses and measurable performance. Training replaced calibration. Conditioning substituted for circuitry. Reliability was achieved through behavior rather than mechanical redundancy. This approach was not metaphorical. It was operational, tested, and validated within the constraints of the time. The absence of combat deployment does not render the weapon irrelevant. Many wartime systems reached maturity without battlefield use due to shifting priorities, resource reallocation, or the emergence of alternative solutions. The Pigeon-Guided missile belongs to this category. It represents a path taken far enough to demonstrate viability, then abandoned when institutional preference and technological momentum shifted elsewhere. In the broader context of World War II, the missile underscores the extent to which the conflict functioned as a laboratory for total warfare. Every discipline capable of contributing to military advantage was mobilized. Boundaries between civilian science and military application were systematically eroded. The Pigeon-Guided missile exemplifies this process with unusual clarity. Historically, the weapon's role is not defined by destruction, but by demonstration. It demonstrated that guidance did not require electronics. It demonstrated that precision could be achieved through biological means. It demonstrated that military research in the 1940s was willing to operationalize any reliable mechanism, regardless of its origin. The Pigeon-Guided missile ultimately reflects the intellectual environment of the Second World War. It was pragmatic, unsentimental, and focused on results. Its existence confirms that the war's most unconventional weapons were not always born from desperation or novelty, but from systematic analysis under extreme conditions. In that respect, it remains a precise representation of how World War II transformed the nature of warfare itself.